I've got two more talks tomorrow, or two more hour-long talks tomorrow, so I'm going to talk about those a bit tomorrow. And today I was just going to focus on shallower systems. So yeah, I just call them supervised embedding approaches, and they're kind of like the simplest feature learning you can do, where we're going to learn just kind of like these embedding vectors for words or for image patches, and then we're just going to like linearly combine them. So there isn't any like sigmoids in this or anything like that, but it's, you know, it's kind of like, it's still feature learning, I think, so it sort of fits into the title of the summer school, but it's kind of like the simplest thing you can do. And I think, you know, that should be kind of like your feature learning baseline, these kind of approaches, before you try, you know, a more multi-layered system, and it can help to understand what happens, you know, before you add the other layers. So yeah, I did quite a lot of work on these algorithms for different applications, and so I'm going to like talk about two of them today. The first part of the talk is about using them for document retrieval. So we're going to be learning hidden representations for words, and the second part is for image annotation. So you have to label images with words, and in particular there's going to be, it's like large-scale image annotations. There's going to be lots of possible words. You can, like 100,000 possible words you could label with, and yeah, so you need these systems to be really fast to train, and they can do that. And yeah, in particular in the second part, the algorithm is going to be a particular way of optimizing the rank list of words, so to optimize the precision at k, and that makes the algorithm really good. But we'll see that later on. So yeah, so the first part is about learning with word features for retrieval. And yeah, there's a bunch of collaborators working with me on that. You can see their names there. So the goal here is, it's basically, you know, like the classic web search kind of goal. You've got a query, which is a piece of text, and you have a database of documents, which are also text. And we want to rank the database and, you know, show the top ones. So you know, Google's really interested in this, obviously, and so the sort of the really dumb baseline is just no learning at all. You just do something like count the number of matches, right, between the query words and the target document words, like as a bag of words. And you know, that's called a vector space model, and you can do things like normalize the counts, like if you heard of TF-IDF, and things like that to try and improve it. Or you can do some learning. So when you do learning, there were, you know, many works that typically try to build a few hand-coded features. Like, for example, one of the features would be the TF-IDF matching score between the query and the target text. That would be like one of the features. And another feature might be like the match in the title, or, you know, and like look at the different parts of the document and count the matches. And then typically there'd only be some small number of these features, and then you would like learn the weighting of them. So, but what we're going to do here is not something like that, hand engineered like that. We're going to be learning like on the words. We're going to learn embedding vectors for every word, but in a supervised fashion. So, you know, things like LSI, latent semantic indexing, also learns from words, but unsupervised. And we see in the experiments that that's a lot worse than doing it supervised, perhaps unsurprisingly. So this is just to show a bit of notation. Which way? Yeah, so as I was saying, with the no machine learning method, what you do is you take your query Q and one of your documents D, and you represent both of them as bag of words, right? So D is our dictionary size, and so this is a big sparse vector, right? Lots of zeros, only where you have words will there be non-zeros. Then so the score between a query and document is just the dot product. So this doesn't deal with synonyms at all, so this is a bad idea from that point of view, right? For example, supposing the query was kitten vet NYC and the document was cat veterinarian New York, then you don't actually have any match at all, right? You have a score of 0 because there aren't any words that match if you didn't deal with the synonyms. So that's what something like latent semantic indexing can try and fix, right? In a unsupervised fashion. So what that's going to do is take your original representation, your bag of words representation, and multiply it by some matrix U that projects it into a so-called embedding space, right? Into a low-dimensional space. So this might be something like 100-dimensional space, 200-dimensional space, where you've kind of mixed all of the words together now in this space. So now, in that space, you do your dot product, not in the original sparse space, with the hope of now catching synonyms, right? So if, for example, two words like cat and kitten have similar embedding vectors after the transformation U, then you'll get a higher score for that than for matching cat with some other word like, I don't know, parrot, or something even more irrelevant. So what you're actually doing there is basically just this matrix U. You've got one, so because you're mapping from the dictionary, which could be something like 100,000 down to 200, for every word you've got one 200-dimensional vector that you're learning. And so with something like LSI, you're just doing a reconstruction objective. You don't have query document pairs, you just take documents and you just try and, I mean, it's like the autoencoders probably you've seen earlier, right? Just without any sigmoids. So just a note though, down here is a footnote that says actually to get better performance, you really want to combine those two things, because after you've done LSI and you have these embedding vectors, you've kind of blurred the space. You can't necessarily get like exact word matches anymore, which something like just this really dumb method up here can do. So when you combine the two, you tend to kind of get both the synonym kind of thing, like the generalization from the LSI, and you get like the the memorization, the exact matching from the basic bag of words. So, but here's the model that we suggested in our work as a kind of trying to fix some of the things wrong, which we called polynomial semantic indexing, or polynomial supervised semantic indexing. So the idea is, well, first I'll show like the really most naive model, which is here. We're gonna make a score between the query and document of this form. So we're gonna have this mapping function phi k, which considers all possible k degree terms, so like polynomial terms between query and document words. So if we only consider like k equals 2, then we just get something like this, where we're just going to have a W matrix between every word qi in the query and word dj in the document. So you consider all the pairs and you have a weight wij for each pair. Okay, so this is basically like the full rank version of LSI, right? You know, with something like this example with kitten vet NYC, stuff like that, what you'd want to learn is that, yeah, so the IJ component in W for kitten and cat, you'd want that probably to be something positive, so you get like a matching score there. But we can also consider something like k equals 3. Okay, so now we don't just do pairs of words, we can consider triples. So like the jth word in the document, the kth word in the document, and the ith word in the query. And now we have like this three-dimensional tensor W that we have to learn. And you could have that part plus the two degree terms before, add them together. So why would that be useful? I have a kind of made up example here that you might have, for example, Jagger, the word Jagger in the query and the word Stones in the document. So, you know, this might be a match for the Rolling Stones. But if you had, say, the word Stones and the word Gem in the document and the word Jagger in the query, this might not look like a good match anymore, because these two words together seem to indicate something about like precious gems, you know, so it's not, doesn't look so related to the Rolling Stones music anymore. So you could see that if you had this triple, you might want to, like, you know, downweight. I mean, it kind of looks hard to learn these kind of things, but yeah, but potentially you could. So that's basically the model, and then we're going to train these things supervised. That's the other difference to LSI. So we're going to target that for our goal. We want for a given query document pair that we know is a good match, we want basically this score FQD to be large. We want it to be larger than for things that aren't a good match. So we can learn this thing with like a ranking kind of loss, something like that, which other people have done too, but more often like with these hand-engineered features, like I said, with the small feature spaces. So why is this kind of naive model suck though? It's too big, because so this big W matrix I showed you, like let's supposing we have 30,000 words in the dictionary, it's already like 3 gigabytes it's taking up, and 15 terabytes if we have 2.5 million words, which we will in some Wikipedia experiments that I'm going to show later. So that's the biggest problem, and then the obvious way to fix it is the same way that LSI fixes it, which is just to make W low rank instead of full rank. Like, so just directly constrain it. So I'm only going to learn these matrices U and V. We've done this a little bit different to LSI. Like I was telling you, the mixture of bag of words and LSI together, you know, is better. So we can just put that directly into our model. So if we just, because if you have W equals the identity, right, then you just have, for the 2-degree model, you just have the bag of words like dot product again. You know, you just get back the original vector space kind of scores. So you get like that kind of specificity from there. So we just added that to this part, the low rank part, and yeah, and that's basically it. So now we just have to train that model. So that's for k equals 2. And for k equals 3, you get something similar. Basically, you have to have, instead of just U and V, which U embeds the query words, right, and V embed the document words. You need a Y matrix as well, which there's going to be two ways of embedding the document words. So that's to do the three-dimensional W tensor. So yeah, so that's the model. And if you want to look at it as a neural network, then the degree 2 model just looks like this. We've got our query coming in, which is of length the size of the dictionary. Same thing for the document. These are the bag of words representations. And they go into these two modules and come out as like much smaller vectors that we're going to take the dot product of. This is when you don't add the identity. This is just showing like the UV part of the model. Yeah, so it's what you put in these modules basically will change whether you have like a degree 2 or degree 3. Like if this is just a linear transformation, it's just your one matrix, then you get the degree 2 model. And if that thing, so this here is a zoom up of that module 2 there. If that thing has actually two linear maps, so that would be the V and the Y matrices, and then you do a component-wise product and an output, then the embedding vector for the document, that gives you the extra power of like the three-way interactions. So it's just a little bit more complicated network. And yeah, so then we that's our models. Now we can just train those things, and we just use like a standard ranking loss. I don't know if you all know it. It's basically you would do stochastic gradient descent, and you would pick a random, well, we write it as triplets. Let's say you know a triplet where you know the query D+ is the document that should be relevant for that query, and D- should be irrelevant. Then basically you just want QD+, like the F of QD+, so the score for that pair to be larger than for QD-, and we say that it has to be larger by some margin of, well, 1, arbitrarily chosen to 1. So you can just basically, do I have pseudocode for that? No, but, oh, well, just basically there. Basically, you would just compute FWQD+, compute FWQD-, check whether QD+ is one larger than the other one, and if it is, you don't have to do anything, and if it isn't, then you do that gradient update. So yeah, I think lots of prior work in this area. Obviously, can't possibly cover it all in this slide. I mentioned people doing like ranking loss kind of things with hand-coded features. There's a couple of citations there. In contrast, we're only using words in these models I'm talking about, and we're going to find their hidden representation. And then there's several works on trying to improve the loss function over the ranking loss that I just showed on the previous slide, like trying to optimize mean average precision or NDCG or one of these things that tries to care about the top of the rank list rather than just like the average position. I'm going to talk about that a little more when I talk about image annotation. And yeah, there's some other works that try to deal with having huge number of features like hash kernels that we also compare to in our experiments. So some experiments with that model on Wikipedia. So this was a few years ago where we had around 2 million Wikipedia documents, and the links between them, there's around 25 million links. We split this data into train and test, and then the experimental setup is two ways. One is where we take a whole document and sort of pretend it's a query, and so you want to retrieve all the documents that it's linked to. Okay, so we're using the links as kind of the supervision, but obviously we're hiding some of the links. So we have some of the links in training and some of the links are reserved for the test set. So that's how we can build our triples, our QD plus triples. The D minus, actually, we just select it randomly. We say anything that we don't have a link for, we assume it's irrelevant, and that's how we do the training. And then we have another setup where we just pick 5, 10, or 20 words at random from that query document and say it's like keyword search. I mean, it's kind of also fake, right? Because it's kind of hard to get, or it was at the time we did these experiments, hard to get real data to do, public data to do these comparisons on. So the first results are with a restricted dictionary of 30,000 words, so it's the most frequent 30,000. And we did that so that we could train some models that just can't handle millions of words, like we tried like the margin ranking perceptron. So basically that would be, essentially that would be like our naive model, this one, where we don't have the low rank thing. So you have all like the pairwise weights. So yeah, so TF-IDF is just like the standard bag of words scoring, and then we have different metrics for success. So the ranking loss, that's kind of like the thing that we're training that I showed you, and then there's mean average precision and precision at 10, and so the approach that I've been talking about with k equals 2 and k equals 3 is down here, and yeah, it's performing a little better than the margin ranking perceptron, which is kind of the non-embedding version, right, the full rank version. And yeah, it's much better than not doing any machine learning at all, or doing unsupervised learning, so that's with LSI. Yeah, so that looks good. And then we did with, same thing with a larger dictionary, so 2.5 million words. And all the results, so also for the, the non-machine learning vector space model, and everything gets a bit better. So that was 1.62 before, now it's 0.84. But we still have the same trends, and we tried hash kernels here too. And yeah, just some scatter plots like per query document pair, I guess. Oh no, it's per, is this? No, it's mean average precision, so it's per query. We're comparing our approach SSI with just TF-IDF scoring or with LSI. You can see like the improvements are like across the board, across all queries pretty much. And this was the keyword-based experiments. Again, the same kind of results. Everything's worse, like the ranking loss is worse, but the order of the algorithms is basically the same. So yeah. We also tried doing some stuff with cross-language retrieval. So the nice thing about Wikipedia is in lots of languages, so we took like the Japanese versions of all the query documents and said, okay, we can use that as the query, but we'll have the English documents as the ones that you have to retrieve. So this doesn't actually pose any problem to the supervised learning of these SSI models, apart from the identity part of the model, which is, if you go back, where is that? Like this thing, it's okay. We've got like the embedding U for the Japanese words. So okay, so they're going to have these low dimensional embedding vectors, and we're going to have the V for the English words. but the I will just have 0. There won't be any term matches, but that's okay. It can still learn. And we can compare that to basically using like something like Google Translate to translate the Japanese documents. So now they're in English, and then just using like normal vector space scoring again, which is much worse than SSI. And we can also, this is kind of interesting, if you translate the query to English, and then do SSI, you're actually worse than leaving it in Japanese. So you kind of do better not using a translation tool. And I guess the reason why is because after you've translated, you've kind of, you're not hedging your bets anymore. You've made those decisions, and if they're wrong, you kind of can't go back. But back when you're doing the embedding from the Japanese, I think you can kind of like leave that smooth in a way, so it doesn't make exact decisions, or that would be my guess anyway. Yeah. So yeah, this I'm just going to skip that. Because I have some much nicer, because I wanted to show what's inside the embeddings that you learn, and so these are like, so for the word vet, what's the nearest other words to that word, and but I have some much nicer table for the image experiments. So, but these ones look okay, but they're not as amazing. So yeah, so that's the first part of the talk. So that's a quite nice supervised method for document ranking, which is really simple. And before you kind of try more complex methods for learning representations, I would sort of encourage to use something like that as a baseline. Even though we showed, that when we did add some more nonlinearities, like with the three-way matrix, we did get an improvement. So that kind of indicates using some deeper networks or something like that might get you more as well. Maybe if anyone has any questions or anything, I could take those before I go to the next bit. Not sure I'm really allowed to answer what Google uses, but apart from the fact that I don't know everything they use, but I mean, certainly I think you could see in they have made public basically saying it's got a lot of stuff in it, a lot of signals in it, right? So. The combination of LSI and the backward. Oh, yeah, you would learn the mixing parameter. Yeah, that's what I did here too. Would it be just a linear combination is what I did in these experiments. Yeah, I don't know if you can do better somehow else.
So, what's the largest K that you use?
Here, I only use 2 and 3.
You only use 2 and 3?
Yeah. Okay. So this is like polynomial degree 3, right? Yeah. I mean, I could have used more.
Just curious what would have happened.
Oh, yeah. Yeah, me too. Well, I mean, there are, people doing not exactly that, but like deeper, neural network stuff for text things now. So, I mean, Hugo Larochelle does some stuff. I don't know exactly what. Does he do retrieval? I don't know.
Yeah, so
Oh, and there's your guys too, but Jeff Dean's group, which, yeah.
Yeah, I'm not going to talk about. Yeah, but we do use it for language modeling, which is
not quite the same.
And people have been using neural nets to use as input type of words.
Yeah. So yeah.
In an academic setting, not in practice.
Yeah, but that's all I have here. So tomorrow I'm going to also talk about using deeper neural nets for text, but not for this exact task. It's more for like semantic role labeling, part of speech tagging, named entity recognition. So there's so many tasks. You can always keep playing around. So the second part is kind of similar stuff, but for image annotation. So yeah, so this was with Sami Benjo and Nicolas Rossinier. So we actually saw a little bit of this in Russ's talk. So here, yeah, we have, we're given an image and we're going to have a fixed set of possible annotations, so like maybe hundreds of thousands of these things, and then we're going to rank them. So it's basically, you know, like the last talk, except we're still ranking documents, if you like, but the documents are just like these very small pieces of text now, and the query now is not just a few text words, it's a whole image. So otherwise, it's going to be like similar algorithm. So yeah, and one nice thing about this is it's going to be like a really scalable algorithm for making fast predictions. Maybe you're laughing at Jay-Z or okay, yeah. So yeah, there was these experiments are from a while ago. So ImageNet is like a growing database of labeled images, human annotated images. So they basically took something called WordNet, which I don't know if you all know, which is kind of like a graph of concepts, like disambiguated concepts, and for each node in that graph, they're annotating, basically putting images, saying, okay, those are images of that concept. So it's not even like the word Jaguar or something, it's the disambiguated version. So you have then a node for the car and a node for the cat or something. Anyway, and at that time it was like 2.5 million images, and now it's like, I don't know, is it 16 million? So it's really growing. And well, actually, yeah, sorry, it was 2.5 million for training, and we split it into training, test, and validation, and we had around 16,000 possible annotations. And we also took a data set, like a internal Google data set from image search, some subset where we had 10 million training images and 3 million tests, 3 million validation, around 100,000 possible annotations. So those are the kind of sizes. It was already quite big. Yeah, we're going to use that same kind of approach, and it has some advantages compared to some naive approaches. Like, for example, you could think, okay, I'm just going to do like one versus the rest, like with, say, linear classifiers like SVM or something. So then you need like 100,000 SVMs, right, for 100,000 annotations, and you have to go and, for the image, go and compute all of them and then sort them, or just find the top 10 or something. And actually that can be a little expensive because, well, depending on your feature representation, here we took like a bag of visual words feature representation with like 10,000 visual words, something like that. And so the one versus rest is actually kind of big. It's like 8 gigabytes or something, whereas this low rank thing is much smaller. It's more like 80 megabytes. So you get this kind of advantage and a little bit of advantage in speed terms because you've gone into the low dimensional embedding space. You know, once you're in this 100-dimensional space, you know, those dot products are cheap. So yeah, so that's kind of some advantages. And the new thing basically in this part of the talk is I'm going to talk about how to optimize precision at K to make the results better. So this is just a pictorial thing of what we're doing with the embedding. So we have this 100-dimensional embedding space, that's the thing where we're trying to learn these vectors. So for say the phrase, the annotation Eiffel Tower, we're learning a 100-dimensional vector for that guy. And same thing for Obama and the word dolphin. And then for an image of a dolphin, so we're given this 10,000 dimensional bag of visual words, and we're going to map that down also to the same embedding space. Okay, so the words and the images live in this same joint embedding space, and we want such that when you look for the closest few, say the closest 10, that the right answer is there. So that's where the sort of precision at K comes in. If you're measuring like that, then you don't want to just sort of look on average how far it is, but whether it's in the top K. Yep.
Can you clarify what you mean by bag of visual words? Like, is that just small patches, or?
Yeah, I might have a slide. Oh yeah, I have a slide. So this is something where you segment into overlapping blocks at various scales. I mean, this is just sort of one way. There's lots of different ways. You would represent each block by color and edge features, and then you basically run k-means with 10,000 centers on those things, and then afterwards, when you get a new image, you can cut it up into the blocks in the same way. You look for which center they're closest to from the k-means, and then you would have a 10,000 dimensional vector, and you'd have kind of like the count in each dimension of how many times that block appeared. So this is the kind of thing. So this isn't what this summer school's about, right? We're about like trying to do feature learning, but that's kind of the thing that actually all image people sort of using as a baseline, right? I mean, well, the next thing you do after that is try and take into account the geometry a bit of the image, so that things are in the upper left-hand side, right, compared to the bottom right-hand side, which this thing doesn't. This thing's like analogous to the bag of words from the first part of the talk. This is the bag of visual words. You don't know where the patch came from in the image anymore. You just know that it appeared. The next thing people do is basically split up that space, the new feature space, into parts where you say, oh, did it appear, the number of types of that block that appeared in the top left, and the number of parts that appeared in the bottom right. And this is called like a pyramid match. So that's good. Where are we? So that's what we're doing. So the only sort of feature learning we're doing is not that part, but just this second part of mapping into this embedding space. So we're kind of only doing like one layer, if you like, of representation learning, and leaving the rest. Mark Aurelio, I think, is going to talk tomorrow about ImageNet. Are you not? Yeah, but doing like a more deep network approach to that, so that will follow on. So I think I pretty much talked about everything here. I mean, it's just the same model as before, but I've just written it differently. One thing to keep in mind is that you might need the embedding matrices you're learning, V and W, you might need to constrain them to have some maximal norm. So we actually did that. We said like each one has to be less than equal to C. And if you don't do that, you could have a problem that because you're using a dot product as you learn, these things could explode. They can get larger and larger because our matching score is the dot product in the embedding space. So we also added this constraint. I didn't say that in the previous talk. So this is the same ranking loss as before. We could use that as well. Okay, so now basically we have a query image, and so I've just written it like this, where fy would be the true annotation for image x, and fy bar would be some other annotation, and you'd want that larger. So here's a reason why you wouldn't want to use this loss function. Let's supposing that you had two functions that you were choosing between. One, and there's just two training examples, two functions, really simple. So with one of the functions, the true annotation is ranked first, okay? And in the other example, the true annotation is ranked 101st. So you've kind of, like with precision at k, you've got one of the examples right and the other one wrong. Now function 2, the true annotation is ranked 50th with one of the examples and 52nd with the other example. Now, if you count the number of violations with this loss function, so the number of y bar that are above y, it's the same for both functions. It's like 100 violations. So using this loss function, you don't care whether you pick function 1 or function 2. But you might be interested in picking function 1 because at least it gets one of your training examples right, even if it gets the other one wrong, whereas the other one just gets them both wrong, right? If you're measuring precision at k. If you're measuring some other loss function like average rank, then they're the same. I mean, and that's what that's optimizing. But yeah, but typically we're interested in this top of the list because many applications you're showing those results to the user, right? The ones at the top. So. So we need a different loss function. So this is one loss function you can use that was developed by Asuni et al. In 09 ICML. So they propose this kind of loss here. So the error that you make for a given image x and true label y is basically proportional to the rank of y. And then you compute the rank of y, and the rank is just counting the number of y bar, so negative annotations that are above y. You just count that number, and that's the rank. So you've got that rank, and now you put it through this function L. So after you've got that rank, it's just an integer, you put it through L and convert it to loss. That's the penalty you pay for that particular rank. And now, depending how you choose this L function, you could imagine, because you know all the ranks, you can basically choose any kind of penalization you want depending on where in the list. So you can do things like, instead of, basically if you choose a constant penalization, then you get this thing again. You get just the ranking loss, the AUC loss. So what they proposed was to say that L of the rank K is defined by this sum of alpha j up to k, so up to the particular rank of that example. So these alpha are just things you set in advance, like before training. They define your loss function. So how you define these alpha defines your particular loss. So if you define them as some constant, you get the mean rank from before. And if you make them some decaying thing, like alpha j is 1 over j, so it's getting smaller and smaller with higher rank, then basically you're paying more attention to the top of the list. So so that's the idea of that loss function, which indeed, if you put it through the example I gave on the slide before, with alpha j equals 1 over j, you get, for function 1, you get a loss of 5, and for function 2, you get a loss of 9. So it does prefer function 1 like we want. So that looks good. But problem is, I want to be able to train with stochastic gradient descent, one of these models, like lots of people are doing. But that loss function is kind of it takes a bit of time to compute, and the reason why is because you have to compute the rank. So just to compute the rank, imagine I've got 100,000 labels, right? I have to, just for one example I'm training on in SGD, you pick a random example, and before I even do one gradient update, I need to know the rank. So I need to go through all 100,000 annotations and compute their scores, and then find where the true one is in that list. And that's costly. So I don't want to do that. So basically the trick we proposed was a sampling trick, where you, instead of computing all of them, you basically keep picking, so you know the true label y, okay, so you could compute f of y. Now, I want to know how many fy bar are above f of y. So what I'm going to do is pick a random y bar, just from my set of 100,000, compute its score fy bar, and if it's not a violating label, so if it's not above f of y, then I pick another one. And I keep picking one until I find one that violates. And now the trick is basically that the number of times I had to pick is going to be like an estimate of the rank. Because if you have to pick many times, then you probably have a low rank. F of y is high up the list, right? So then this is this approximation that basically the rank is approximated by the number of labels minus 1 divided by the number of times I had to sample until I found a violator. And so this is only approximate version of the rank. So this plot just shows this would be the true loss on this. Yeah, basically, I want my results to be on the diagonal, and they're kind of like during my SGD they're like dotted all over, so they're not really exactly right. But it turns out that it works okay. So then that's the pseudocode of the algorithm. I basically just said it all, so I don't know if I need to go through it. I think I'll skip this slide. Yeah, so now I'll just show some experiments comparing that model to some other standard approaches. So one versus the rest, like I talked about, and also using a ranking loss with a full rank model, and doing approximate KNN. I should say there's many approaches to optimizing precision at K around, like I cite some here, and this is just one method, but I think this one works quite well on for SGD. So you could use this approach for like any kind of neural network model. So I think it could be quite interesting for that. So yeah, and then these were the results we had back then. Actually, we've got better ones now, but yeah. But this method, we called it Wasabi for like web scale annotation by input embedding, and that was the acronym. And yeah, so this is precision at 1 and precision at 10, which are pretty low actually. But this approach is working better than the competitors by a little bit. And the reason why isn't because of the low rank thing, actually, it's because of this optimizing the precision. So precision at K, so I can show that because if we optimize with the AUC, that's the ranking loss thing, the same model, we get 1.6 precision at 1, whereas if we use this thing for optimizing precision at K, we called it warp for weighted approximately ranked pairwise loss, then you get this almost twice sort of improvement here. But it's it works on the low rank models and on the full rank models. You also get a boost. So and on both data sets. And this slide was just to show, yeah, if you don't do this sampling trick that I talked about, you never get anywhere. Basically, this is time to train, and this is like the test precision. And this is if you do like without the sampling trick, you try and do the computation of the rank exactly. You never get any good test precision because it just takes too long. Much like this talk. And this shows, test time, speeds, and amount of space the different models take. So like I was saying, this low rank thing has a nice advantage that it doesn't take a lot of memory. I mean, compared to something like k-nearest neighbor, it's also really fast. But yeah, these are just different results showing if you change the embedding dimension, you get similar things. We tried some stuff like doing an ensemble of multiple models, and we got even further improvements. But I don't think I want to. And just to say how like features are really important. I mean, which like I told you about the bag of visual words, we tried another thing called KPCA Ensemble, which is like an ensemble of lots of different hand-engineered features, and we got even further improvements. So we went from this 6% P1, which is the best thing we had with our ensemble, up to 10% with this better feature representation and an ensemble as well. So yeah. So that's just to show that basically if you keep these very simple, shallow models, then you're really reliant on your hand engineering. You know, you have to do that well. If you have a deeper network, then maybe you can you're not so reliant on your human expertise about vision problems, because you can learn those representations. But then, you know, you're reliant also on the expertise of your modeling ability of your neural net researchers. So yeah, this was a little bit nicer embedding I wanted to show you. So this is after learning the image annotation task. You could look for any given annotation, which are the closest annotations in the embedding space, and those look pretty nice in general. So this is on web data, so you actually get like different spellings and like misspellings and things like that. So that's what's happening there. These were just examples of the annotations. Yeah, you already saw that one. And like this radioactive, it's kind of, yeah. So yeah, so that's basically it for this talk. So yeah, overall, we have some nice algorithms for ranking annotation. If you want to keep your method really simple, you just want to learn like embedding vectors, but you don't want to do like deeper networks. So, but on the other hand, you're kind of a slave to how good your feature engineering is, as you saw with the bag of visual words and KPCA representations, changing the error rates really significantly with the same algorithm. So, you know, you can only do so much changing the loss function, like the precision at K thing that I showed here. I think what, you know, you really need to do better is to learn the representations, and, you know, that's more the subject of this meeting. And yeah, in my next talk, I'm going to talk about deeper networks for text tomorrow. So yeah, so that's it.